Amplifiers. An amplifier is a device whose primary function is to convert the amplitude of an electric signal. It can also be used to alter the frequency of an electronic signal. Last year we looked at the creation of a load line for transistors. Take note that we can use the same methods and the same procedures to develop the load lines for junction field effect transistors, metal oxide semiconductor field effect transistors, as we did for the bijunction transistors. Now, thinking back, we would have a positive supply that would connect to a resistor. We're going to call that RC, or our collector resistor. That would go into my transistor, and then we would have that connect to 0 volts at the bottom. The transistor would then feed into my input voltage, which at this point is 0, and then we would have a base resistor connected to the transistor's base in order to allow for biasing of that transistor to take place. This collector resistor is there to serve as a voltage divider of the supply along with the transistor, so that we could develop an output voltage across that transistor. It also serves to limit the current through the transistor. Now, if we think back to the transistor's output characteristics, we would recall we would have all those lines going out like that. Each line represented a different base current. Vertical axis would represent my collector current, and then my voltage across the collector emitter would be represented on the horizontal edge. Now, in order to determine the load line, the first formula, or the first concept I need to remember, is the maximum voltage that can develop on the collector emitter occurs when the transistor is completely off, which means it acts like an open switch, which means the overall voltage will be seen on the transistor as there's no current flow throwing through my collector resistor. So VCE intersect is equal to VCC, which is the supply voltage. So let's say that point is indicated on my graph at that point over there. Next is the calculation whereby we look at what is the maximum collector current that's going to flow through my transistor. Now, if we look at this, we can say this is the point whereby the transistor is going to be completely on, whereby it's got 0 volts across itself, and as a result all the voltage will be seen on the collector resistor. So the formula is IC is equal to VCC divided by RC. Now, if we add resistors below, emitter resistors and such, then we need to incorporate those values into this formula as well. So this point over here will be indicated somewhere on my vertical axis over there. And by joining those 2 points, I will get my load line. Now, the load line will be dependent on a specific circuit as well as the specific transistor that's going to be used. If I decrease my supply voltage, the angle will remain the same, but the position will change. When I change the value of the collector resistor, this point is going to stay the same, but the gradient of this line is going to change. Now, the Q point determines the state that the transistor is in when there's no input signal connected. In other words, It determines the gain of the circuit when it is at rest. To calculate the Q point, or the Q point value, we use the formula IB at Q is equal to VCC minus VBE divided by RB. We have to remember that this transistor serves as a divider for two parallel circuits. We've got the first circuit that runs through the collector resistor, and we've got the second circuit that runs through the base emitter junction as well as the base resistor. Now, the base resistor's voltage will be dependent on the supply voltage minus that voltage across the base emitter. Now remember, if this is a silicon transistor, that voltage is going to be 0.6 volts, and if this is a germanium transistor, then that voltage is going to be 0.3 volts, and that is going to be replaced in that variable over there. Now the Q point, we would then, if we were to indicate it on the load line, our value over here, we would find the corresponding value for the base current, and where that base current graph meets the load line, that is where we would indicate our Q point, somewhere on that line. Now the Q point will determine what class of amplifier I am working with. The different classes of amplifiers will determine the characteristics of those amplifiers, but we will go into more detail on those aspects in the next video.